Hello, in this video, we're going to be looking at lesson 6.5 on conditions for special parallelograms. In the previous lesson, 6.4, we talked about the special properties for special parallelograms, where we looked at properties of rectangles and rhombuses. In this section, we're going to look at how do you prove that a quadrilateral is a rhombus, a rectangle, or a square. There are two different conditions that we can use to prove that a parallelogram is a rectangle. For our first theorem, theorem 651, if one angle of a parallelogram is a right angle, then the parallelogram is a rectangle. It's really important that we understand that this only applies if we know that the figure is a parallelogram. So if I know that we have a parallelogram and we have one right angle, then the parallelogram is a rectangle. If you'd like to abbreviate this theorem, you can say parallelogram with one right angle, arrow rectangle, or you can just call it theorem 651. The second condition for rectangles is if the diagonals of a parallelogram are congruent, then the parallelogram is a rectangle. As before, this theorem only applies if we know that the quadrilateral is a parallelogram. You can abbreviate this theorem with the theorem number 6-5-2 or with parallelogram with diagonals congruent, arrow, rectangle. So now that we have these two conditions for rectangles, let's go ahead and apply this to a carpentry application. A contractor built a wood frame for the side of a house so that XY is congruent to WZ and XW is congruent to YZ. Using a tape measure, the contractor found that XZ equals WY. Why must the frame be a rectangle? The first thing that I would recommend that you do here is mark what's given. We're given that XY is congruent to WZ. So that is the top segment and the bottom segment, and also that XW is congruent to YZ. So that information right there, we have both pairs of opposite sides of the figure congruent, so we know that it has to be a parallelogram from what we learned back in section 6.3. Here I summarized what I wrote. As both pairs of opposite sides of WXYZ are congruent, so WXYZ is a parallelogram by theorem 6-3-2. We know that if a quadrilateral has two pairs of opposite sides that are congruent, it must be a parallelogram. So now that we've proven that it's a parallelogram, we can use one of these two conditions to prove that it's a rectangle. And for our next piece of information, we have that the contractor measured and found that XZ is equal to WY. Notice that XZ is a diagonal and WY is also a diagonal. Since XZ is equal to WY, we have the diagonals of parallelogram WXYZ are congruent. And we know now, if we apply theorem 652, that if a parallelogram has congruent diagonals, then it's a rectangle. Therefore, WXYZ is a rectangle by theorem 6-5-2. To summarize what we just did, we first had to show that it was a parallelogram. Then after we showed that WXYZ was a parallelogram, then by showing that the diagonals were congruent, we were able to make the conclusion that it's a rectangle. Now we're ready to look at some conditions for rhombuses. There are three different conditions we can use to prove that a parallelogram is a rhombus. For the first condition, which is theorem 6-5-3, if one pair of consecutive sides of a parallelogram are congruent, then the parallelogram is a rhombus. You can abbreviate the theorem like this: parallelogram with one pair consecutive sides congruent, arrow rhombus, or it's probably shorter if we just call it theorem 6-5-3. The second condition for a rhombus, theorem 6-5-4, is if the diagonals of a parallelogram are perpendicular, then the parallelogram is a rhombus. You can either abbreviate this as theorem 6-5-4, or you can do parallelogram with diagonals perpendicular, arrow, rhombus. The final condition for a rhombus is if one diagonal of a parallelogram bisects a pair of opposite angles, then the parallelogram is a rhombus. So notice in our picture here, we have this diagonal FH, and notice how FH is bisecting the angles so that all four of these little angles are congruent. So anytime a parallelogram has a diagonal that bisects opposite angles, you can conclude that it's a rhombus. Now that we have those conditions filled in, let's go ahead and look at an application. In example 2, we're going to apply the conditions for rectangles and rhombuses to kind of write a proof. We're not going to do a formal proof here, but we're just going to try to decide if the conclusion is valid. If it's not valid, we'll tell what additional information is needed to make it valid. So the first thing we need to do is read the given and mark the givens in our picture, and then see if that's enough information to make the conclusion here valid. So in this first problem, we're given that AB is congruent to CD, and BC is congruent to AD. So that just covered the first two givens. And then the next given is AD is perpendicular to DC. So here's AD, here's DC. If those are perpendicular, that means that's a right angle. And then the last condition here in the given is AC is perpendicular to BD. AC and BD are the diagonals, and if they're perpendicular, that's a right angle right there. We want to see if the conclusion ABCD is a square is valid. And anytime that you are trying to prove something's a square, you need to be able to show that it is a rectangle and a rhombus. Because to be a square, it needs to be both. All of the conditions for rectangles and rhombuses that we've discussed in this section have started with parallelograms. So the first thing we need to do to determine if this conclusion is valid is to see if we have enough information to show that ABCD is a parallelogram. So for step 1, I'm going to start by showing that ABCD is a parallelogram. Now, the first given that I underlined here in red gives us that AB is congruent to CD and BC is congruent to AD. So we have both pairs of opposite sides that are congruent, and that's enough information there to prove it's a parallelogram. So here I just summarized what I stated. Since AB is congruent to CD and BC is congruent to AD, both pairs of opposite sides are congruent, and ABCD is a parallelogram by theorem 6-3-2. That's one of the conditions for parallelograms that we learned in lesson 6.3. Now we need to check to see if this parallelogram is a rectangle. So looking at our conditions for rectangles, there are two. One of the conditions states that if one angle of a parallelogram is a right angle, then the parallelogram is a rectangle. Since AD is perpendicular to DC, that gives us angle ADC is a right angle. And if we look at condition 1 for rectangles, it says that if a parallelogram has one right angle, then it is a rectangle. Therefore, parallelogram ABCD is a rectangle by theorem 6-5-1. So now that we've established it's a parallelogram and a rectangle, we just need to show that it's a rhombus. If I can show it's a rhombus, we can show it's a square because a square is just a quadrilateral that's both a rectangle and a rhombus. Well, the last condition here is that AC is perpendicular to BD. And that means the diagonals are perpendicular. And if we look at our conditions for rhombuses, we'll see that this is one of them. Since AC is perpendicular to BD, we have the diagonals perpendicular, and therefore, parallelogram ABCD is a rhombus by theorem 6-5-4. So now we've shown that it's a rectangle and a rhombus, so we can determine that it is a square. Since we've shown that ABCD is a rectangle and a rhombus, we know that it has 4 right angles and 4 congruent sides. Therefore, ABCD is a square by definition. The definition of a square is a quadrilateral with 4 congruent sides and 4 right angles. We've shown that, therefore the conclusion here is valid. Let's try one more example here for this day 1 portion of our video. This time we're given that angle ABC is a right angle. So let's mark that in our picture. Angle ABC, so that's this angle right here, is a right angle. And we want to know, can we conclude that ABCD is a rectangle? If you look at your conditions for rectangles, one of the conditions states that if a parallelogram has 1 right angle, then it's a rectangle. However, in this problem, we do not have enough information here to conclude that ABCD is a parallelogram. So we cannot use that 1 right angle to conclude it's a rectangle. Therefore, this conclusion is not valid. So we have to be really careful when using these conditions. This is not valid because we do not know that it's a parallelogram, and that condition that involves 1 right angle proving that it's a rectangle requires it to be a parallelogram. The directions state that if it's not valid, tell what additional information would be needed to make it valid. We would need to be given that ABCD is a parallelogram, and if we know it was a parallelogram, then we would be able to use theorem 6-5-1 to conclude it's a rectangle. So the first part of my answer here is stating that the conclusion is not valid and why, and the second part states what additional information we would need to make the conclusion valid. This concludes the first portion of lesson 6-5. We'll do the final example in the 6-5 day 2 video. Thanks for watching. Bye.